Good afternoon, GM Lerner here, country manager for US for ComSys. I'm sitting here in a very historical location with Christian, and I don't think I need to say that we are electrical geeks here, especially in this location. So this is a pump house since 1888. 1912 it got electrified, and behind us here we have single phase transformers, 110 kVA each, uh, supporting this pump house. So very, very interesting. What do you say, Christian? You were kind of very, you see your eyes glowing for this place.
Oh, I like that. It's a really nice historical location, and you see all the installation that is happening here with the old pumps. Nothing is running anymore, unfortunately, but it's great to have that converted into a cafe. So that's a very, very beautiful thing here.
Yeah, so whoever knows where we are, put it in the comment bar and see if you know where we are. So we were not just chatting here about this, but we were thinking go a bit more into IEEE 519, and it's a very interesting topic here. So Christian, what do you think we should start with?
I think it's a good point to start on the IEEE 519 just to discuss about a few important topic on the IEEE 519. We have a few names, a few things that are only used in IEEE 519, and it's good to understand what they actually mean, because there's still a lot of people that are misunderstanding the IEEE 519.
Yeah, I totally agree. The interpretation, PCC or terminal of the component that's installed. So there's a lot of things out there that kind of misunderstands.
Correct. And let's start directly with the PCC. I think the PCC is already a very important point to discuss, because the IEEE 519 specifies harmonic on the PCC level only. Even now in the latest edition, in the 2022 edition, they really write it very specifically that these limits are not to interpret the target levels on the equipment. It is really for the PCC level. And PCC is simply the point of common coupling. And point of common coupling means it is the location where the grid operator is giving over the electricity to the consumer. That is the location. So typically it is the meter position. So if you have an energy meter, wherever you have that energy meter, that is usually the PCC level.
Yeah, so I would say for a product that we manufacture, active harmonic filters, it gives us and the customer an opportunity to customize for the utilization factor of the whole system. So instead of putting mitigation right at each component in the single line one diagram, it gives you opportunity to just put one module in and take the whole system. So totally agree.
Absolutely. And actually, if you read through the IEEE 519 a little more in detail, you will actually figure out that the goal on the IEEE 519 is not to protect your equipment. The goal on the IEEE 519 is to protect your neighbors from your equipment. So it of course makes still a difference where you put in compensation equipment. So for example, if we put it on the PCC level, then we actually only protect the equipment, especially if we have the PCC level on the primary of the transformer. If we connect the compensation equipment, however, on the secondary of the transformer, we can do both. We can protect the equipment itself from the harmonics, but we also protect the neighbor from the harmonics that you would create.
I think we can agree on that IEEE 519 has the right intention here. It sounds good. But when we maybe dig a bit deeper, we maybe have some comments.
Yeah, the intention is very good, and absolutely, but we should look a little bit deeper. And I think the next topic that you should understand when we're talking about the IEEE 519, that is the maximum demand load current. The maximum demand load current is used for a lot of different factors in the IEEE 519. And you can imagine a very simple way. You can simply say your maximum loading that you have in your facility, that is your maximum demand load current. That's the maximum demand that you have to the grid operator. There is, of course, some minor tweaks, minor differences. So technically, you would need to measure it for 1 year, and then within 1 year, you can figure out the average, and that is your maximum demand load current. But we don't need to go that much in detail. We can leave it on a basic level and say roughly the maximum loading on your equipment is the maximum demand load
I
current.
think it's a very, very good way of seeing it. So if you have a lot of load, you will have a percentage of this in distortion, and it's a big distortion. And if you have minimal load and the distortion is higher percentage, it's not really that much for the system. So I agree in there, but here I think the most misinterpretation happens where the consulting engineers doesn't know. He doesn't know the system, so he cannot put the demands on the component to keep this PCC level.
Yeah, that is actually a very difficult point on the IEEE 519 because it's a system standard. You should theoretically know the entire system with every load, with every transformer, with the grid conditions. All these things you need to know to make a very good assessment of the situation and to figure out if you're complying with the IEEE 519 or if you're not complying with the IEEE 519. And we know that is very, very difficult to do, absolutely. But let's go to the next topic, I would say. Let's talk a little bit about total demand distortion. So if we look in all other standards in the world, all standards working with something that's called the THDI, the total harmonic distortion in the current. And this total harmonic distortion in the current is calculated very simple. We're just taking all the harmonics, put them together in an RMS. So we are squaring each of the harmonic order, we're summing them up, then we take the square root. This value, this is the harmonic current that we have in the grid. That value we're dividing by the fundamental current. And that's a pretty good idea because, I mean, having an amp value there is not always that good. It's sometimes better to see it in a percentage, and this THDI would give you a percentage. However, the big problem that we have with the THDI is that this fundamental current that can vary all the time. It can go a little bit up, can go a little bit down, and the harmonics might stay the same. So in that perspective, it is not always the ideal solution. So the IEEE 519 already a long time ago came up with a very good solution on that. So if we look back at the maximum demand load current, if we always take this maximum demand load current and divide by that instead of the fundamental current, we will get a better value. So if we take the IEEE 519, we're taking again the harmonic current, sum up the entire harmonic current, we're dividing it by the maximum demand load current, and we're getting a new value, and that value is now the TDD, the total demand distortion.
Yeah, and this is huge. This is where end user can save a lot of money. And all now in the trends of ESG and so forth, this can be in your goals to really save money and have a system that is optimized for you. So this is, if we can get the consulting engineers to adopt this and get the information from the beginning, we will save hardware and get better systems. So really, really interesting.
Correct. Unfortunately, we still see a lot requirements where they say we want to reach IEEE 519 with a THDI of 8%, 10%, whatever it is, but we don't need to reach a THDI level. We need to reach a TDD level, and that can make quite a difference.
Yeah, and it's interesting you're saying that. We see power quality meterings from very, high-level utility companies that order these measurements, and they are not measuring towards the total demand distortion. So this is a big change that needs to happen if we're going to have an optimized system.
Yeah. Of course, if we are at full load or if we're at demand load, then the THDI and the TDD is essentially the same value. In all other conditions, it's not the same value. And we can see that in a very nice graph over here. So we have here a graph, and we're having in black the fundamental current, and in blue the harmonic current. And you see the harmonic current and the fundamental current is just rising up over time. Now, if we go in the traditional way with the THDI, we would always take the harmonic current and divide it by the fundamental current at every point in time, and what we're getting is this red line. So we see a big up and down, a swing, it sometimes really bad, sometimes really good. So it's just a zigzag, a random noise more or less. And it looks like this over here with close to 70% is the worst case situation, which it is not, because if we look at the load is actually very low in this condition. So it cannot be the worst
So high
situation.
percentage doesn't mean it's bad. It's where we are in the load situation. That's
Correct.
why total demand distortion is so important.
Correct. And if we now say we have a total demand current of 1200 amps, and we divide this harmonic current always by the 1200 amps, what we're getting is this green curve with the TDD. And this TDD level follows exactly the harmonics.
Yeah.
And now we can see over here at this point, this is the worst case scenario. This is where we have the highest amplitude in the harmonic current. We actually also have the highest amplitude in the fundamental current, and we have the worst case situation.
Yeah.
And here we see that the THDI and the TDD, they are coming together, because we are now at the maximum load condition where the THDI and the TDD is the same. All the rest of the time, the THDI and the TDD is not the same.
I will borrow your cursor here. So if you're looking on the system that are normally placed in the systems today is passive filters, and they are dimensioned for this point up here. We, with active harmonic filter, just handle the compensation current down here. Huge difference. So this is really what we will try to get out to people and the consulting engineers.
Absolutely. Otherwise, we can talk a little bit about the standard itself. So IEEE 519, what does it mean? What does this? What levels do we need to reach in this standard? And you know what we hear typically from the customer. I want
5%.
to have 5% IEEE 519, and this is of course not the case. IEEE 519 doesn't say it always needs to be 5% in the current. This is something that some marketing people came up with and really pushed it out that it's always 5%. Of course, it's easier, but it's not quite the truth. If you look into the standard, you will see that the main goal for the IEEE 519 is a voltage distortion. So we want to limit the voltage distortion to below 8%. Exactly what we said before, to protect your neighbor, because the voltage distortion is visible at your neighbor's place as well, not only at your place. The current distortion is only visible at your place, but the voltage distortion will travel over to your neighbor.
But I would say this is where I'm getting, a bit questionable on the IEEE 519, because it's really the voltage distortion that will harm your equipment. Yeah, current distortion is not good, you can hit cables and so forth and breakers. But the limitation you see in this chart really makes us to oversize also the active filters for the systems. We're going to reach 2-3% with the limits you have in the chart to the right on the current distortions.
That is right. And if we look at these limits here, you can see that these limits are depending on the short circuit ratio. So that is the ratio between the short circuit current of the grid, and that can be the primary side of the transformer grid, so whatever the grid operator is supplying to you, or it could be the secondary side, so whatever is limited by the transformer, and we divide that again by the maximum demand load current. So you see the maximum demand load current is picking into all of these different aspects, so it's a very important
so
factor.
You probably hear about the stiff network or soft or weak network. This is really what it is. So
Correct.
if you have less than 20 here, then you have a weak network, and then they put in a harder demand on the current distortion. Or if you have a very stiff network, meaning that the transformer is very oversized to your load, then you can allow a lot of current distortion.
Correct. So we can see here 20% THDI, or to be say 20% TDD, is absolutely allowed in the IEEE 519. So we don't have to reach 5% all the time.
Yeah, so in theory, misinterpreting this can give you an 80% higher dimensioning of the products to mitigate the distortion. Quite a lot of money to save here, and room area, sizing area.
Absolutely. And as you said already, if we really look at these harmonic current levels that we should reach, if we reach these levels, typically what we're seeing in the field is that we are reaching a THDU of 2 to 3%. So we are reaching a much lower THDU level than the IEEE is actually specifying. So with these current limits that we have in the IEEE 519, we are very, very strict. So this limits the harmonics to a very large degree. If we compare that to other countries in the world, they are way more relaxed on that level. So most other countries are specifying on the voltage level. And of course, what you want to do is you want to avoid a too high THD level, because that increases the risk of failure and the reduction of lifetime of your equipment. But you don't want to go way too low in this level as well. Otherwise, your power quality solution will be very, very costly. And we want to avoid that as well. So somewhere here in the middle, we need to have a sweet spot where we say this is a good position where we put our target level, and that's where we should go. Unfortunately, this curve here is an exponential curve. So if you have 1% or 2%, that's more or less no difference. But if you have 10% or 11%, that makes already a very big difference.
Yeah, that's a question I often get when I'm out, where? And it's really on the line here, the vertical line here to the right. It can happen very, very fast and cause a lot of damages to measuring instrument and expensive robots or your production. So when you're over 8%, we can say for sure you're gonna have problems. Between 5 and 8, yeah, if you don't have a problem, you don't have a problem, but there could be problems already there. Under 5%, not many really have any bigger problems.
And the other way around is as well the case. So if you're down at 5% voltage distortion, that doesn't mean you will never have problem. It just reduces the overall risk for you having problem. And if we then look around in the world, what the different standards are, we see most of the standards are going in the voltage distortion, and most of these standards also put the level somewhere around 8%. So if we would now interpret the IEEE 519 to be 8% voltage distortion, we would be similar in the compensation need as in Europe. But in Europe right now we're seeing at least half of the compensation need compared to the US, and that is because the US is going so strongly on the current limits of the IEEE 519 to make sure that everything is so way down in the voltage distortion that it's very, very expensive to do a compensation.
Yeah, so it would be very interesting what you listeners think about this. We're quite harsh against IEEE 519, how it's written right now. Intent is perfectly good, but then the current distortion levels are really easy to misinterpret with the levels, so it would be better to go with the voltage distortion level. So any last words?
I think everything is said that needs to be said.
Yeah, just enjoy this atmosphere here, and I hope you feel the geek electric atmosphere here with us. So thank you for listening, and any comments, please let us know.
Thank you.